much for the introduction and also to the invitation. This is about perfectoid rings, not perfectoid spaces, I should say, right away. This is motivated by what you find on the webpage of the lean formalization of perfectoid spaces. So here are the perfectoid spaces, and up there are the perfectoid rings as a kind of important component of perfectoid spaces. The upstairs part only amounts to, I would say, I didn't count it, but 20% is my feeling of the whole lean formalization. So I think I should be rather modest in terms of mathematical achievement here. Lean uses this imperative proof style. I've taken something out of the middle of proving here, and this is the kind of proofs you see. So you have something like A is small, B is small, and then the product of A and B should also be small under some criterion. And the proof basically tells you nothing if you read it. I think you only can understand it if you are, first of all, in the matter, and then also you have to read it interactively and see on the right-hand side of your screen what the present goals are and how you sort of discharge them. Now here, in contrast, is something from the Naproche formalization, and I think the style of proof here is, first of all, in natural words. It is sort of readable, and it is the kind of reasoning you would see in limit arguments in analysis. Yeah? So take an epsilon, or give me an epsilon, then I find a delta, maybe I find another one, and so this is the kind of argument here, and I would think that if one looks at it longer, we haven't got the time here, then one would sort of understand what the sort of limit argument in this context is. So I wrote this natural language formalization of perfectoid rings. It's not yet completely polished, again emphasizing rings instead of spaces, alas. So the whole thing is a LaTeX document which can be loaded into the system, and the usual way I use Naproche is through the Isabelle proof development environment. So on the right hand side you would see the LaTeX header of the thing, and then on the left hand side you see what comes out of it. So I very much emphasize LaTeX here, and also natural writing in LaTeX, so that you can semi-formally write things very freely. Of course, the title and the abstract is freely formulated, and then embedded in there, you would find formal things. So here's the outline. First of all, quite a lot of preliminaries. It's a self-contained document, no big library imported. So all these things are sort of developed from the egg. Sets, numbers, finite sequences, and then the algebraic structures that are of concern here. But this is all very general on the left-hand side, and then it goes towards these perfectoid rings by sort of specializing the rings more and more until you are there. So we get to something which is a literate style, thinking of literate programming, or it's semi-formal or flexi-formal, I guess, but I have to talk more to Michael about this. So the text would look like, the printout would look like that, where you have, and this is something which is missing on this display, you would have that things which are formal are on a gray background. Yeah? If you don't believe it, come forward to my laptop, look at the gray background, and also where I have signature up there below the axioms, that's a gray box background box, so that the formal parts and the informal parts are clearly distinguishable in the display or in the printout. Yeah. And you can see that this is sort of the source for the left-hand side, for example, in the middle, so this is there's under axioms, there's begin Fortl, so we enter a Fortl environment, which is this official input language here, and then it goes on in the Fortl environment, and probably here you would find an end Fortl, then we can write something as we like, then another begin Fortl until the end. So you have this checkered text, which you can't appreciate on this display, unfortunately, of free and then of more formal things. So, on gray background, you would find the upstairs definition 290 of Perfectoid's rings, and I compare it to what Peter Scholze has written in one of the articles about this field. Okay, so that's the end. How do we get there? So very sorry about the background, but definition 290 is on.
So is the top line, is the quotients, blah, 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 is that also part of Naproche? Or only the
good question, yeah. I cut some corners here, right? Because I just want to get to this result, and I wouldn't do anything with a Perfectoid ring or so. So this is defined via modulo. Yeah. So right, I will show you later. So how does one find a formal grammar appropriate to this situation? This is again Peter Scholze's definition. You see a natural language or a mathematical natural language statement here. And how would you analyze it linguistically? Well, you would perhaps try to find a grammar appropriate to it, and perhaps you would see this is the definition of a predicate, and then that consists of a head, where the new thing is introduced, and then the statement, which is the condition, the property here. And the if is something that you would find up there in the text, and this is sort of a terminal, nothing further analyzed in the grammar. So if you go through this, you find the predicate head, you find the if, and you find the rest of it as one big statement. And now you want to go on, of course. So look at this statement, R is complete, uniform, and so on. And then if you look at it, this statement, well, it looks like a chained statement, and the type of chain is an end chain. There are maybe OR chains, other kinds of chains, commas, and so on. And what is an end chain? Well, it seems to connect primary statements through this terminal word, and that, of course, you find several times up there. So here's the and. That's the only and which is actually of interest at the moment, because the other and, that is in the such that subordinate statement there. Okay, and then you can go on and you look at primary statements, and it seems that the there is, what there exists is what sort of characterizes the statement very much. So we have to do with the there is statement, and it can start with there and then exists, singular or plural, and we are very free and don't care about grammar. So grammatical correctness is really something that the author has to care about, but in the parsing, a lot of things are just identified for simplicity. Yeah, okay, and then it goes down to notions, and notions are a very important, the central grammatical category here, because notions correspond to nouns. In German, nouns are even called Hauptwörter, so they're really the main words. And so somehow the grammar is built up around these notions. But notions can be complicated. So the whole yellow thing upstairs is one notion, a pseudo-unifier with certain properties, etc. And on the other hand, nouns in natural language, of course, correspond to informal types. And so notions are the types of the system that we're using. Notions can be very complicated, as you see here. So our notion checking, for example, the type checking here amounts to often rather complicated first order proving, which has some disadvantages, of course.
There is a question. Pardon?
Sorry?
Yeah, a little question. I think this is very interesting. How do you decide that the and belongs to the notion and not to a higher level?
I try what the parser translates.
Yes.
I look at the first order rendering,
Yes.
and then I see, okay, it puts the brackets in the right places.
So you get two parses initially, and then you choose the one that is better semantically, right?
Well, as the thing is set up, it gives me just one parse here,
Okay.
because the such then sort of it makes a big bracket around the rest of it. And also, if you look at it, there's only that way to interpret things correctly, because the is that an upsilon, the omega with the thing on top? Yeah. It's upsilon.
Pi, actually, I think.
Sorry?
It's a weird pi, actually.
Pi. Okay, the weird pi. The weird pi is it exists, but then it's also used in the second part. So the quantifier has to go.
Yeah, no, that I can understand, but I just wonder if the grammar is so you do it.
Yeah, it's a question what we define as the range of a quantifier. Yeah.
Yes, so it is.
It seems to go long, so to speak.
So you might have a grammar that makes this ambiguous, because the and could also bind on a higher level.
Yeah.
But then you would look at the semantics.
But then you have a problem. Yeah, but we don't do it like that. There are just sort of heuristic rules. Actually, I should say these grammar rules here are taken over from Andrzej Paskiewicz, who is with us. And I'm very thankful that he helped us in sort of taking over the SAD project from him. And so this happened several years ago, and we are still using basic structures, basic algorithms from there. Yeah, so if you look through the grammar, you would find that how it would sort of bracket things.
But then in some other text you might have and you might need a grammar rule where and belongs to a different level.
Yeah.
That is not applied here.
Not in this case, no.
Okay.
Yeah.
Okay.
And if you have sort of an unwanted reading of such an end,
Yeah.
and you have to worry, maybe you can restate the thing. Also, in serious cases, you are even allowed to put brackets into the text. Okay. Yeah. So these grammar rules are taken from an introduction to Fortel by André. There's a whole long list of grammar rules. We have extended that, and these grammar rules have been implemented by André in the original SAD program, and the grammar rules are sort of, I mean, this is more or less an orientation. In detail, the rules are a bit more complicated, and many of them, that's what we have in the Naproche system now. Okay. So, when we have sort of, I mean, you read off from the mathematical literature or from your example a lot of desired grammar rules, and then they define a language, the language of accepted sentences. And the question is, can we then come near to the natural language we started with? And so, as you've already seen, the approximation that Naproche at the moment offers is, well, we can't write the original sentence, but sort of, well, it looks like a rewording, so to speak. Yeah. So, for example, the assumption that we are talking about Tate rings up there is sort of taken out, and R is pre-typed as a Tate ring here, and then some of the things are more or less word by word, but then we don't have the commas. The IE construct is probably rather difficult because IE might mean various things according to its content and so on. So that's the approximation here. And here is just a listing. For reasons of time, I can't very go through everything, but I want to emphasize that, in my view, natural language here is built around nouns. These are the things that are sort of standing somewhere in a, let's say, mini world, and then these are sort of connected and modified by adjectives, by such that sentences, relative sentences, and so on. We have, as in natural language, two kinds of noun phrases, and let me emphasize phrases. So I'm not just talking about words, but sort of compounds like natural number, two-word phrases, or more complicated phrases where variables can stand in the middle of words, an element of X or so. There are definite nouns, usually in English, the something, the square root of X is something definite, and then there are indefinite nouns, and the indefinite nouns, of course, correspond to types, a natural number, the type of natural numbers, and then with a the, you sort of single out a specific one. In Forte, these types are called notions. You can introduce them by certain commands, and these commands are LaTeX environments at the same time. The interpretation, the semantics is first order. I don't want to go into it too much, but I'll show you a little picture about that. Here is the history that I've already mentioned, and we are still working at it with difficulties and all sorts of experiments, etc. So, let's go into the formalization. So I will show you just some sort of pieces. As you imagine, the more technical thing is on a gray background. These are sort of system commands, read-in commands. Of course, you could think of a natural language way of saying that, let us read in reference number so and so, but at the moment it's just in this technical form here. So we import some vocabulary, and this is just to show you how simple the linguistics here is. We just identify the word factor and the word factors because we don't want to do anything with grammatical number here. So a lot of things are thrown together. It's a very simplified approach to a language. There are not just single words, but there are these kinds of phrases. So a phrase which is already there is element of X, but perhaps we want to denote it differently. So we say a member of X can also stand for an element of X. And this is just to introduce a grammatical variation. Of course, this is problematic because it sort of depends on you or us how much variation is introduced. Actually, these things can be introduced in a text or maybe in a sort of read-in extra file to a text, so it's up to the author how much of these extra things are introduced, and one has, of course, to worry that doesn't lead to ambiguity and so on.
Do you have antonyms?
Sorry?
Do you have antonyms?
No, not like, I think Misa has, right? Yeah.
What was the question?
You have antonyms.
Antonyms.
Antonyms, yes. Okay. So, let's look at another snippet from the text. So, as I said, everything is done from first principles. Natural numbers are introduced. Mathematical objects, that notion is already in the system. And then I can say a natural number is a special mathematical object. And thereby, first of all, introduce the type of natural numbers and also introduce that it's a subtype of the type of objects. As we know from set theory, not everything should be an object. So certain things like proper classes can lie outside the objects. Okay, then second line, some pre-typing. Here is the formation of a class. We do the collection of natural numbers. Instead, I could write set brackets all n such that n is a natural number. Here comes, this is just because it goes like that in the text. The axiom of infinity is just the statement that n, the class that we just introduced, is a set, but we don't do much with set theory in this document. So 0 is introduced, so this is a definite noun in a symbolic form. And then also we introduce here the plus function, and it's introduced as a typed function because we know that m and n have their types, natural numbers, and the result is also a natural number. Yeah? So we have introduced in natural words a typed function here, and then here is the first axiom, and it goes on like that. So how would we interpret this first order? So I like these kinds of pictures. So here on the right-hand side, big bubble is all the objects. Other big bubble is all the classes that I could form in my class theory. So there's a rudimentary class theory, rather a notation, I would say, built into the system. And if you want more set theory, then you have to write axioms, like the infinity axiom. Then classes and objects intersect in the sets, but I'm not requesting that every object is a set, although as a set theorist, originally I had this tendency. So momentarily the numbers lie in indefinite way probably outside of the sets, and they are this structure I indicated there, and then as a set they fall in this middle intersection. Yeah, so that's the first order interpretation. You could also look at a first order translation, but I rather do it with our main sentence there about Perfectoid and so on. And you can look in the output when the parsing happens. An output window shows you the process, and it shows the translations therein. And you see how this is translated. And you also see that there exists a v0. So we are working with the Brown variables here. So the name upsilon, or funny pi, goes away and is replaced by v0, and then the quantifier ranges from here to the end, so that that explains this sort of interpretation of the middle end there.
How do you introduce the first order equivalence of this fancy elliptic notation? Like the TP predicates, like do divides in, within, etc.
Oh, this is just taken from some definitions. Yeah? These words, I mean, there was perhaps a definition which says divides x in Yeah, you might have some phrase basically, which goes like, I just have colored chalk here. Sorry about that. Green on green. Yellow. Yeah. So A divides B within or whatever. C also. You define this somewhere via definition. So a new relation, this division relation is introduced. It goes by this phrase, which goes from here to there. The phrase has 3 holes where terms can be inserted, and then the divides within also. This is somehow concocted into one word, just to have an internal symbol for it, and the do is written in front because it's sort of like a verbal relation.
So this is fully automated?
Yes. Yeah, this is not invented by me. Doesn't look good.
The divides is actually a symbol in this example.
Sorry?
The divides is a symbol. It's a middle.
Yeah. Right.
And I guess it also calls
Yeah, but this is sort of by alternative phrases, yeah. So perhaps it was introduced using the word divides, and then I introduced another phrase just as a alternative, which uses the division symbol.
If it was introduced with the symbol of that.
I think there's a difficulty introducing things symbolically and wordy at the same time. So I rather introduce things in one way or the other and then do my variations sort of by defining synonyms.
Well, I mean, like for the naming, like what do you do when there's?
Oh, yeah. Then the symbols are somehow squeezed into ASCII. You can't see these things at the moment, but sometimes very funny words, ASCII words, come out of it. Because then something like backslash is a BS, and these things are then concocted or some artificial name. Yeah, right. So binomial coefficients are important. Why are they? Because there is this thing with the Frobenius isomorphism somewhere, and here's the yellow chalk. So we want to study something like x goes to x to the p a prime number, and we also want that x plus y basically goes to x to the p plus y to the p. This is of course wrong, and so this should be modulo p, and so that sort of you can forget the middle bits of the binomial expansion here. They are all divisible by p. That requires some work. So therefore I have to put some energy into these binomial coefficients. You can see here that I don't have a good definition mechanism for recursive functions, but they are just introduced as a new symbol by a signature command with a little typing there. And then we have 2 axioms which explain the recursion. Of course, this could be made better. We also have some function definitions available within proofs, but we haven't sort of pulled it onto the level of, onto the top level, so to speak, at the moment. Okay, so you can see here a little proof, and it's proof by induction. So proof by induction does something with the thesis that you have at the very moment. Here's the thesis of the lemma, of course. Yeah, maybe that's the thesis. And then this thesis is sort of, when I say by induction on K, it is reduced to something, well, I could say roughly the process of doing complete induction. It's a bit more complicated and more elegant, but that's too much detail, I think, for now. Yeah, so it looks a little familiar. You do the case k equals 0, but then that is trivial. Now, trivial sort of finishes that case. Then you go to another case. We know now that this case assumption, or this case assumption is negated. So we can actually form the predecessor of K and use the induction hypothesis on the predecessor to do our little argument here. And it uses this thing that if a prime number doesn't divide one factor and doesn't divide the other factor, then the prime number doesn't divide the product. This primality. Okay. We have to talk about groups and rings and so on. And here is a very naive approach to structures. I'll just say a group is a set, as you might find in quite a few books, of course. And then this set, which is sort of gets the attribute, I'm also a group, gets some other elements. So, for example, a zero, a plus operation, and so on. At the moment, they are all denoted as these upper G's, so that you know that they belong to the group. But then this becomes annoying that you have all these G's around. So when you prove that minus minus x is x, it's decorated with all these G's, as you can see up there. And so, just to get around that, I use LaTeX. Yeah, I said I want to emphasize LaTeX here. And this is a very dirty LaTeX trick, which makes the sort of the what is it? The head, this caret, also makes that sort of like a backslash, like a command character, and then you can define, and that's this funny LaTeX definition there in the middle. It's sort of when you emit this this command, then from there on in a LaTeX text, the upper G is, or whatever is up in this bracket here, is just left out. Right, and so it looks better, right? This is the idea. Minus minus x is x, and here's a little argument. Not very elegant because we don't have good parsing for arithmetical operations. Could, of course, be introduced, so that a lot of brackets are needed in algebraic computations.
But you still have to write in your LaTeX sources the upper, the caret G, right?
Right.
Okay, good.
So the source is the source. It has complete information. We have no elaboration on things, so it's all there. But you could say what we see printed out is kind of a nice picture, a pretty printing of the source, including leaving out certain things from the source. We run into further algebraic difficulties. You already can see difficulties here in such a proof because you see the main brackets, as I mentioned. But this is still okay, but these difficulties sort of increase further, and you get into some kind of algebraic hell. This is not even a complete proof. The idea is to show something that's the lemma here. This lemma is sort of, well, we want to work towards a binomial formula, which is one of the we-like theorems as well. So we want to work there, and so we take partial binomial sums. That's when you look at the upper thing of this lemma 195, and then you multiply it with x plus y. And so this partial sum is that if you go in the Pascal triangle, you do some sums and then there is a remainder or so. And so it's quite an unpleasant thing. But the more unpleasant thing is to how much detail at the moment it seems I have to go to make this argument going. Yeah? So this is just a weakness of the system because we don't have proper term treatment or no SMT for that.
4 minutes included.
Oh, right. So let's see. Topological spaces we know all. Here is the outline again. We have gone through the left-hand side, the preliminaries. And now, how do we go towards perfectoid rings? So here's some mathematical background. Think of Galois theory. Think of perfect fields in Galois theory, which are important, etc. But from the formalization standpoint, what we have is a big tower of definitions. We follow the lean formalization. Thank you. I think without, I couldn't have done it. And then there are definitions along the way which have to be justified. Let's say quotient or so. And the difficulty of single proofs is not so bad. I think it's similar to what you find in algebra or analysis lecture courses. So main property is boundedness, being small here in various ways. And so here is what a bounded subset is. It can, by multiplication, be compressed into arbitrary small arbitrary small neighborhoods of the zero. Yeah. That's sort of like an epsilon delta property. And then you want to show a lot of boundednesses, and you say, for example, that powers of an element, R to the n, formed in the ring R, these things together form a bounded set. So yeah, there is a little set theory, because this is a set, and you can form it because n is a set. So it's a question how much set theory actually gets into the picture here. Right, and then you want that small sets, as I said before, multiplied are small again, power bounded in this case. All power bounded form this subring R0, and indeed it is a subring if you have an extra assumption here. And then you sort of specialize your rings. Yeah? A Huber ring is something which has, where the topology is generated in a certain way. And in such rings, the R0, the little things that we want to concentrate on, behave correctly, like a subring. And then there are Tate rings, which have a specific topologically nilpotent element. So nilpotent is, of course, that, I don't know, x to the 5 then equals 0. Topological means in the limit goes to 0. Yeah? The powers go to 0. That's the definition of topological nilpotency. And then a Tate ring is a Huber ring which has a pseudo-uniformizer, topologically nilpotent, which is also a unit. And then the Frobenius that already was mentioned can be formed within such a Huber ring. So we fix a prime number and we do the function that I indicated. We check that the result of the function is still in R0, so it maps R0 to R0. And then let me go to this slide. Then actually this mapping, this phi, respects calculations modulo pi or modulo pi to the p. That is what you find in the property in the Peter Scholze article. But it's defined via modulo. Here is some more about how I use or misuse LaTeX to get certain graphical effects. And here are some conclusions which I skip, and thank you very much.